into uh, lower order and higher order bar elements. So the lower order bar elements used linear shift functions, and this one use quadratic shift functions. And then you had two nodes per element over here, and there you had three nodes per element. We also realized that if the distributed load is absent, then the linear shift function gives you accurate results. Although you are looking for approximate solutions, that's what a numerical method is. And but if we have linear shift functions, then we can also have accurate results when the distributed load is zero. And this one gives you accurate results if q is a constant. If say even if q is non-zero and still a constant, this would probably give you an accurate result. Now, with this line of thinking, we can realize that we can also come up with bar elements with cubic shape functions. Now, why are we interested in cubic shape functions? The shape functions essentially map how the primary variable, in this case the deflection, changes along the across the element. So if this is the coordinate measured along the element, the physical coordinate, and this is the displacement degree of freedom. So the variation, okay. So I'm trying to show cubic polynomial with this one. A cubic polynomial will have a separate maxima and minima, and sometimes they also get merged. For example, if we're dealing with x cube, so the minima and the maxima, they get merged over here. Okay, so maxima from this side and minima from this side. So but they have two of them in general. Now I can come up with 4 degrees of freedom for a single element, namely u1, u2, u3, and u4, while I could number them as n1, n2, n3, and 4. And then I also have devised with our understanding, we have also devised with our understanding of Lagrange polynomial a method to get the shift functions. The conditions on shift functions, summation over I equals, so there would be 4 nodes, so 4 shift functions, 1 to 4, summation ni equals 1. And in I, xi j at the jth node should be delta ij, which basically means 1 if I equals j, and 0 if I not equal j. So again, I can have my xi mapped from -1 to 1, and then this could be -1, minus 0.25, 0.25, and 1, right? So I can split that into three equal parts. No, this is not three equal parts. Should be -1 third and +1 third. Okay, and this is how the shift function should be. For example, I can construct, let's say, in 1. Okay, now the value of in 1 is 1 0 0 0. Okay, so it should be 0 everywhere except for node 1. Okay, so it's a cubic polynomial, everywhere it is 0, and the way it achieves identical values at three locations is by going through this sort of this sort of variation. You see, this is the only way you can have three identical values on a single polynomial. So n1 could be something like, since it is 0 if, in each of these uh, values, so xi plus 1 third, xi minus 1 third, and xi minus 1. Now if you substitute xi equals -1, what value would you get? You'd get, if I put a negative sign, of course, in the beginning, so this becomes minus 2 third, then minus 4 third, and minus 2. So in the end, you have 2 third times 4 third times 2. So it is 16 by 9. So why not multiply everything with 9 by 16? So you have 1. There is a fourth condition that you are supposed to satisfy. So we have this understanding to come up with the expression for n1, n2, n3, and n4 for a bar element with cubic shift functions. Okay. So all I'm trying to say here is, this point onwards, we have enough understanding to go with cubic or fourth order or any order, fifth order polynomial, okay, as shape functions. So nothing is stopping us from there. But in all commercially available FE software, and everyone who has some experience in finite element method would probably stop at quadratic shape function. Okay, so higher order bar element exclusively means quadratic shape functions. Why only quadratic? That is a question that we would try to answer in this class. But before we start answering it, do you understand the question?
No, sir.
You do?
No, sir.
You don't understand the question.
No.
So the question is, why would anyone stop at only two variations of the two versions of the bar element, either linear bar element and or quadratic bar element? Why not go for even higher order polynomials? That's the question that I'm trying to pose here. So
Sir,
most finite element software does that. Sorry.
sir, just one assumption. Is it like that if we increase the complexity by bringing a cubic or higher order equations, and
Mhm.
the result we get is not so much, it does not have much change compared to a quadratic shape function?
Well, one thing for sure, that let's take the example of bar element itself. Okay, even with this simplest case. So imagine if your q is something like sine hyperbolic of alpha times x. This is not a polynomial. This is an exponential function, and that means that means no amount of polynomial upgradation can ever trace this exactly. Can ever trace the effect of this sort of a q exactly. Okay, so of course, once you go for higher, that being said, once you go for higher and higher order polynomial, okay, you are getting more and more accuracy. There would never be a case where your quadratic shape function bar element would be more accurate compared to, I mean, as long as the element size is the same. If you are modeling the entire bar with a single element, considering that as the case, it will never be a case that your linear bar element would be more accurate than the quadratic bar element, or the quadratic bar element would be more than, let's say, the one we do not go for, which is the bar element with cubic shape functions. It will never be the case, because you'll have to think in this way that if you let u to be something like c0 plus c1x plus c2x squared plus c3x cube, okay, then you are also allowing it to be a quadratic polynomial just by setting c3 equals 0. And because it is allowing, so all I'm trying to say here is set of all quadratic functions, okay, is a subset of set of all cubic functions. Okay, so there is no way this would be more accurate compared to this one. That is assured. Okay, even with an exponential loading, okay, probably this would give you more accurate result compared to this one. But that's not the point. Okay, and getting the accurate solution has never been the point, because it's a numerical method. We just show as an observation that with no distributed load, the linear shape function gives you accurate result, and with uniform distributed load, the quadratic shape function gives you accurate result. That is, those are just observations. Okay, but those are not criteria. Okay, but that being said, the cubic shape functions will always be more accurate than the quadratic shape functions, and those would be more accurate. Both of them would be more accurate compared to the linear shape functions. Okay.
Yes, sir.
Yes, sir.
Now there is one more way we can introduce more degrees of freedom. Degrees of freedom in this case, u, nothing else. Okay. So one way of introducing more degrees of freedom for the same geometry is to go for higher order polynomial. And at this point, I just get confused whether it is called P refinement or H refinement, but I'm going to write it as P refinement. As you see, if I go for from linear to quadratic, I introduce one extra degree of freedom because I introduce one extra node. Okay. And degrees of freedom are always associated with the node. There is one degree of freedom per node. So three nodes, 3 degrees of freedom. Okay. The other way to do that is to mesh through mesh refinement. And if am not wrong, then it is called H refinement. You should definitely check what these two terms mean. I just get confused. So now let's see what I'm doing. I'm modeling the same bar. Okay, same bar as in the bar which is fixed in the left, free in the right, free within quotes. So then you have a concentrated load at the free end, and then you also have a distributed load, but then that distributed load could also be changing along the axis. So it's a function of x. And for this, we had the following differential equation: u being the deflection of anywhere on the bar, then ea u prime plus q of x equals 0 is a is a differential equation, comes with boundary conditions gamma in gamma u 0 equals 0 in gamma t e a u prime at l equals p. Okay, so this is a strong form that we have established probably three classes ago, and then we have also gone the got the v statement for this one, which basically says তো বোঝাই যাচ্ছে true for all v true for all v satisfying v equals 0 in gamma u. Wherever value of u is given, known, v should be 0. Now, we have earlier divided the geometry using three nodes, and then we had used quadratic shape functions. So again, I'm just numbering those nodes, and these are called global numbering. But this time, I'm creating two elements, 1 and 2. I'm dividing the geometry into two elements. Need not be equal divisions. Okay, it's not mandatory. But let's say if I am dividing them into LE1 equals L by 2 equals LE2. Okay, element length 2. So now for this one, please understand, at node 1 there is U1, and node 2 there is U2, at node 3 there is U3. Okay, this term, this integration e a u prime v prime dx on element 1 is essentially, we have established this earlier, v1 v2. So v1 v2 and v3 are essentially the variations of u3 u2 and u1. Okay, of course v1 is 0, but that we will use later. u1 is v1 is 0 because u1 is given. But let's say if I take element 1, that is the lower order element. How do I know that? There are two nodes, 2 degrees of freedom. Essentially, I can construct a polynomial only with two coefficients, which means I can only construct linear polynomials. Essentially, it's a linear shift function, the element with linear shift functions. So a lower order element. And then I have E times A times LE1, 1 minus 1 minus 1, 1 times U1, U2. Now this integration, so over the element 2 would be, in this case, v2 v3. So this basically is your v hat transpose ea le2, 1 minus 1 minus 1 1 u2, u3. And if I do this integration from 0 to L dx, that would be the first term plus the second term. Now let me tell you what's happening over here. You have a vector of size 2 cross 1 multiplying a matrix of size 2 cross 2. You are getting a vector of size 2 cross 1. You have transposed a vector into a row vector, a column vector into a row vector by making it 1 cross 2. So in the end, you are multiplying a 1 cross 2 vector with a 2 cross 1 vector. So in the end, the product is a some sort of a dot product or a scalar. Okay. So that's why it looks like this integration, which is a scalar. Now, can you expand the expression involving write down all the terms in this. Can you simplify this expression? কি বলছি বুঝতে পারছো?
ইয়েস স্যার, মানে এটাকে বেসিক্যালি এটা যে কনভার্সন মানে পুরো ব্রেক করে যেটা বেরোচ্ছে।
হ্যাঁ, মানে এটাকে সিম্পলিফাই করো।
হ্যাঁ।
Write everything involving whatever is multiplying v1 plus whatever is multiplying v2, something like that.
ওকে, মানে এই লাস্ট ইকুয়েশনটা তো আমার যে মানে ইকুয়েশনটাতে দুটোর
হ্যাঁ,
অ্যাডিশন।
the first one, this one,
আচ্ছা, অনলি দ্য
this
ফার্স্ট ওয়ান।
one. হ্যাঁ, and then repeat the process for the number 2.
ওকে।
So in the end, if I write the expression for 0 to L EA u prime v prime dx. So after you get these expressions, okay, for example, for the second element, it is v2 times something in the brackets, then v3 times something in the bracket, okay. So after writing their expressions, and final expression would be v1 times something in the bracket plus v2. Now I'm making a bigger bracket because I believe v2 is there in both the elements, so it will have a lot of terms. And finally, v3 times something within the brackets. Now v1 would only come from element 1 and v3 would only come from element 3. v2 would have terms from both element 1 and element 2. So can you tell me what expression do you get multiplying v1?
Yes, just calculating it.
And for V3, I guess, now
স্যার ওটা ইউ টু মাইনাস ইউ থ্রি হবে না ভি থ্রির সাথে যেটা আছে?
see V3 would multiply with the second row, right? Second row,
ইয়েস স্যার, ইয়েস স্যার।
which would be minus U2 plus U3. তোমাকে কোনো স্টেপ জাম্প করতে হবে না। I I jump steps because I can. You should go through all the steps. And I also have limited space. I cannot show all the calculations on my screen.
স্যার ভি টুর জন্য 2u2 মাইনাস u1 মাইনাস u3।
এই যে 2 বললে না, তাতে
আচ্ছা
প্রবলেম
ওখানে
হচ্ছে you
ই
have
এ বাই
substituted you have substituted uh, the expression for LE1 and LE2.
LE2, হ্যাঁ রাইট।
No, don't do that.
ওকে
Keep them as LE1 and LE2. Okay.
ওকে ওকে ওকে, তাহলে তাহলে মানে জাস্ট এটা ওটা আলাদা হয়ে যাবে, মানে ই এ বাই LE1 u2 প্লাস ই এ বাই LE2 u2 মাইনাস ই এ বাই LE1 u1 মাইনাস ই এ বাই LE2 u3। একটু লম্বা আসছে স্যার ইকুয়েশনটা।
Okay. Now, now I have written down EA by LE1 and etc. But you could simply be doing K11, K12, etc. So you could be calling this one as the element stiffness matrix 1, and then the ijth component of those. You can also be writing the expression in using those notations. Okay. But whatever you do, in the end, this is what you are going to get. This time V1, V2, and V3, they are multiplying, or are in a dot product with the respective terms that are there in the brackets. And you see this V1, V2, V3. Okay. Earlier we had regarded this vector as the V hat vector. And now you would refer to as that the V hat vector of the element. And this one is actually transpose of V hat G, where V hat G is V1, V2, V3, global variation vector. Okay. Now we'll see how is that notation useful. Okay. Now if I also do some manipulations, for instance, if I write this thing to be plus 0 u3 and this thing to be plus 0 u1, then I can also take the u global u hat vector, which would basically be u1, u2, u3, and put a matrix in between. And this matrix would be, can you fill up this matrix? Of course, on the first one, the coefficient of u3 should be 0. On the last one, the coefficient of u1 should be 0. Or in other words, k13 and k 3 1 terms would be 0. Why? Because the first degree of freedom and the third degree of freedom, they belong to different elements and they never get to interact with one another. For example, when you are measuring strain in one of the elements, then it is u2 minus u1 divided by x2 minus x1, and u3 doesn't play any role. So the strain on the first element is totally independent of u3. Okay, and that's why these terms, and same can be said that about epsilon 2, which is u3 minus u2 divided by x3 minus x2. So that also doesn't depend on u1. That's why these terms are 0. Remember, you are not constructing a quadratic shift function, you are not constructing a higher order element across the three nodes. You are constructing two separate lower order elements. Now this term, of course, is EA LE1. What is this term? What is the coefficient of U2
So
on the
minus EA by LE1.
okay. ऑटो शिफ्ट जो ना तो इशू है ना. And this one, because it is going to be a symmetric matrix, because
Yeah.
it comes from a symmetric form. You see, this is the symmetric bilinear form that we have been repeatedly talking about. So it has to be symmetric. Okay. Now I'll go to the second element. That means I'll go to the coefficients of V3.
V3
So coefficient of U1 is 0. Coefficient of U2 is minus EA
by
divided by
LE2.
LE2. And this one is plus
EA
EA
by L.
divided by LE2. And because this is symmetric, so this term is also minus EA LE2. And over here you have EA LE1 plus EA LE2. Okay. And this thing we would refer to as the global stiffness matrix. So far, we are having element stiffness matrix, element degrees of freedom vector, element variation vector. Now we have everything global. Okay. And essentially, if you look carefully, this is what your global stiffness matrix looks like. So whatever degree of freedom belongs to more than one element, okay, the terms get added. Now, this is something you would not encounter in 2D, but in 3D, for example, if I have a triangular element, 1, 2, 3, then I would have 2, 3, 4. And this time, for each node, you will have 2 degrees of freedom in 2D. So there is, let's say, U3 and U4, U5 and U6. Then this one is U1 and U2, and this one is U7 and U8. Okay. You see these two nodes, 2 and 3, that belong to both the elements, element number 1 and element number 2. And when you are constructing the global stiffness matrix, not only you see the degrees of freedom that are shared by two elements are U3, U4, U5, and U6. And when you are constructing the global stiffness matrix, not only your K33, K44 terms get added from both the elements, but also your K34 terms and K43 terms and K53 and K35 terms and so on, they also get combined uh, from either element. So terms from either element gets combined. Okay, because all of these degrees of freedom, these 4 degrees of freedom, belong to either element. Okay, and if there are more elements, for example, if node 3 is shared between element 1, 2, and a third element 3, then for degrees of freedom u5 and u6, the contributions would come from not only node element 1, element 2, as well as element 3. And that would not only happen to the diagonal terms, but also the off diagonal terms. Okay, but more on this later. But this is how the assembling works. So this process is called assembling global stiffness matrix. And this is just this is just forming the left hand side of the variational form. And what you have so far gotten is the global variation vector, transpose of that, the global stiffness matrix, and times the global degree of freedom vector, which is the left hand side. ওকে, এই অবধি বোঝা গেল কি হচ্ছে?
Yes, sir.
ইয়েস স্যার, এটা বোঝা গেছে।
বোঝা গেছে তো?
হ্যাঁ হ্যাঁ।
আচ্ছা। On the right hand side, you have two terms, integration 0 to L q v dx plus p times v at L. Now, if you look carefully, p times v at L, according to our formulation, is going to be p times v3. কোনো অসুবিধা নেই তো এটা বুঝতে? If the two elements span the entire length of the bar, so the node 3 corresponds to the x coordinate. So
Yes, sir.
yeah, so the x coordinate is 0 over here, le1 over here, and L over here, and Le2 is simply L minus Le1. Okay. And if it is PV3, এটা বুঝতে যদি অসুবিধা না থাকে, অসুবিধা থাকলে বলে দাও।
না স্যার, বোঝা যাচ্ছে।
বোঝা যাচ্ছে তো?
Yes, sir.
Can I also write it as this dot product V1, V2, V3 times 0, 0, P
Yes, sir.
ওকে, তাহলে এই সেকেন্ড টার্মটা নিয়ে কোনো অসুবিধা নেই, ফার্স্ট টার্মটা নিয়ে অসুবিধা থাকবে না। ইফ আই রাইট ইট অ্যাজ E1 QV dx plus E2 QV dx. Now Q of course can be some arbitrary function of x, so I don't have any general expression for that one, but we had written earlier that this one would be V1 V2 Q times n transpose across the first element dx. Then there is V2 V3 multiplying integrated over E2 Q times n transpose dx. Now Q is some function of x, okay, and this could be a parabolic function or sinusoidal function, whatever function, okay, but this n transpose, as you know, would simply mean 1 minus xi divided by 2, 1 plus xi divided by 2. And let's say q is a linear function in x. Okay. Let's say it is c1x. So while performing the integration on the first one, this is how we are supposed to represent q as a function of xi. You see, it is c1 times n1 x1 plus n2 x2. Now, for the first element, element 1, q is simply c1 because x1 is 0. It is simply n2, that is 1 plus xi divided by 2 times le1. Okay. But when it comes to second element, it is c1 times 1 minus xi divided by 2 le1 plus 1 plus xi divided by 2 times L. Okay. So be careful with this coordinate transformation. You need to transfer everything into function of xi. Otherwise, because your n is a function of xi, okay, how do you do that transformation? Then you can write dx to be le2 divided by 2 times d xi. Okay. So that we have done earlier. So that this one is basically the Jacobian. But once I do this for each and every element, okay, this whole integration, whole definite integral is fq for element 1. And this whole integration is fq for element 2. That is the force vector due to the distributed load. So in the end, this integration right here is v1 times fq1 1 plus, see, it's a vector of two components, right? Because n is 2 cross 1. Once you integrate each of this with respect to xi, you would get another vector, right? So v1 times fq1 1, v2 times, so the superscript is simply representing the element and the subscript is component. Then you have v2 times f2q1 plus v3 times f2q2. So again, you can club these two. And therefore, you can write this expression as v1, v2, v3 multiplying fq11, fq12 plus fq21. Now, when I say components, do not confuse them with x and y components. They are not Cartesian components. It's not as if the one is along x direction, two is along y direction, because we are solving an uniaxial problem, okay, where there is only one direction, there is the x direction. Okay, these are only corresponding to two nodes of a given element or two degrees of freedom of a given element. Okay, so um, later on we would realize that we don't really treat x and y components differently. Okay, we simply number them, and this numbering, for example, if this is the node number 1, 2, 2 and 3 over here, always counterclockwise. So this has 2 degrees of freedom, u1 and u2. This one has u3 and u4, and this one has u5 and u6. So when I say components of u vector, Then I have U1, U2, U3, U4, U5, and U6. And you realize that U1, U3, and U5 are in X direction, U2, U4, and U6 are in Y direction. Okay, so the components here do not mean in direction. Component is just a numbering. Okay, and that's what is finite element method. So keeping track of your degrees of freedom. Okay, and it's basically an operation in which you need to handle a lot of data. Okay, that's what is most numerical methods and finite element methods especially. Okay, so the third component is essentially F2Q2. Okay, again, if you think about it, if I only had one element, this would be the force vector due to the distributed load, and this would be the force vector for the second element. And they just get combined for the degree of freedom which has been shared between two elements. So they just have an overlap at the degree of freedom that is shared between two elements. That is the U2. Okay. Um, so now if I এই অবধি কি বোঝা গেল কি করা হলো, এই ফোর্স ভেক্টরটা এরকম কেন হবে বোঝা গেল?
জি স্যার, ফোর্স ফ্যাক্টরটা বোঝা গেছে।
ওকে, যদি বোঝা গিয়ে থাকে কিছু আর বোঝার বাকি নেই। সো ইন দি এন্ড উই হ্যাভ so we would refer to this force vector as the global global distributed load force vector. Okay, and this one is again, as you can see, is V hat G transpose. This one is also V hat G transpose. So if you combine everything, the left hand side and the right hand side, this is what you would get. We can take V hat G common, then we have the global stiffness matrix multiplying the global degree of freedom vector minus the global force vector of the distributed load minus 0, 0, P. And by setting left hand equal to right hand side, so this is essentially a dot product that is equal to 0. And as we have done this previously, we can again expand this into a dot product, which would be something like V1 times, let's say, I am writing just the first one, kg 1 UG 1 plus kg 1 UG 2 plus kg 1 UG 3 minus FG Q1 minus 0 plus V2 times corresponding terms, then V3 times the corresponding terms equal to 0. Okay. When it comes to V3, it would be like K31G UG1 plus K32G UG2 plus K33G UG3 minus FGQ3 minus P equals 0. Okay. Now again, we can refer to as that V2 and V3 are arbitrary. Okay. But V1 is 0. So basically, this entire multiplication is 0. But then V2 and V3 are arbitrary, which means I can take V2 equal 1 and V3 equal 0. Then also this sum should be 0. I don't have any control by changing V2 and V3. I'm not changing whatever is inside. But if I choose V2 equal 1 and V3 equal 0, then also this expression is 0. And if I choose the otherwise, that this is equals 0, and this is just 1, then also this whole expression is 0. The only way that is possible is whatever is inside the bracket, that should be 0. But because I cannot say that about the first equation, so basically I'm now able to construct a equation for each row of this system except for the first one, because for the first one I do not know how much this quantity in the bracket is. Okay, because v1 is 0, there is no way for me to argue that for any arbitrary v1 this expression should be 0, and that is only possible when the term inside is also 0, which I could do with v2 and v3, but I cannot do that with v1. And because I cannot set that equal to 0, and he at this point it should feel to you like deja vu, because this is exactly what we discussed in the last class. So if it is not 0, it is something, right? So let's call it R, the residual. As it turns out, this is also the reaction force. And therefore, there are indeed 3 equations to solve for. Although this matrix is not invertible, it's only invertible when you take the 2, 3. So once you take this, what is it called? This is invertible. Okay. So if you take this submatrix, only that is invertible. But the whole matrix is not invertible. We have argued this why? Because if this was invertible, then by applying some arbitrary force, okay, you can calculate u1, u2, and u3. But as it turns out, not all of them can be evaluated. One of them must be given. So if u1 is given, then u2 and u3 can be calculated. Okay. So that spring argument, that the spring could be anywhere and be in equilibrium. So nothing is preventing it from having, let's say, you, let's say, if the force in the spring is k times delta u, then nothing is preventing it from having a displacement u0 plus u0 plus delta u. So this u0 is arbitrary and can be any value, infinite, finite, any value. Okay, so the point I'm trying to make here is that although it's a system of 3 equations, so the 3 unknowns are not u1, u2, and u3. The unknowns are u2 and u3, and the third one is the reaction force for the known degree of freedom, that is u1. Whenever you have a known degree of freedom, you would have a reaction force or reaction moment. Reaction moment when the degree of freedom is a rotational degree of freedom. Okay, so by doing this, you can solve for u2, u3, and r. Okay, এই অবধি কি বোঝা গেছে? বোঝা যায়নি?
স্যার এই আর এর পার্টটা মানে মানে রিঅ্যাকশন এটাকে আমি কি করে কনসিডার
বুঝে
করব?
গেছে একটু হালকা হালকা, শুধু একটু আর দেখতে হবে একবার পুরোটা।
Okay, first of all, I'm not calling it reaction force. I'm saying, as it turns out, this R, the residual, eventually is found out to be the reaction force.
ওকে
Okay. For example, if you do not apply any Q, you only apply, this was one of the assignments. If you only applied P, okay, you would see this R becomes minus P.
ওকে
Okay. So I'm just assuming that the coefficient, so whatever is V1 multiplying, the terms within the bracket, okay, if I cannot definitely say that should be 0, if I cannot say for sure that is 0, then that is something, some positive or negative
সামথিং
quantity.
ইয়া
That something is R.
ওকে
And it can be shown that R is essentially the reaction force corresponding to the known degree of freedom. So wherever you fix the degree of freedom, একটা ক্যান্টিলিভার বিমের যেটা ফিক্সড এন্ড,
Fixed end.
সেখানে একটা রিয়াকশন ফোর্স, একটা রিয়াকশন
একদম।
মোমেন্ট থাকে,
হুম।
because the displacement and the rotation is constrained. If you have a
Constant.
simply supported beam, both ends are prevented
Okay.
from tangential movement, but rotation is not prevented. So you only have reaction forces at the two ends of a simply supported
Simply
beam.
supported beam.
Okay. So I hope this part is also clear to everyone.
Yes, sir.
Yes, sir.
Okay. In that case, you have two assignments for the day. Assignment one. So L equals 1 meter, A equals usual 10 to the power minus 4 meters squared, E equals 200 GPa, and then P equals 100 Newton, and then Q is actually Q0, which is 100 Newton per meter. Okay. Solve with two lower order bar elements and compare with exact closed form analytical solution. You see EA U double prime plus Q equals 0. And if that Q is just 100, you can easily double integrate that. So getting the exact solution is not an issue here. Again, we are not doing it to get the exact solution. Okay, we are just devising a method to get approximate solution to more complicated problems, and we are simply benchmarking them with simple problems like bars. So as you can see, the exact solution would require u to be a quadratic function of x, but here you are considering u to be piecewise linear functions. Of course, u1 is 0, so you are, you know, only allowing piecewise linear function, and the exact solution is a parabola, and this is the finite element solution. At this point, you are now in a position to get finite element solution. So take two lower order bar elements of equal length for the sake of simplicity, and see how far you can trace the exact solution. Okay. Um, so is this assignment clear to everyone?
Yes,
Yes.
sir.
You see, on this side, the stress should be sigma, and on this side, the stress on the bar should be sigma plus sigma prime dx, and together this should provide enough force for centripetal acceleration. So sigma f, the summation of forces in x direction is sigma prime dx times a, and that should be mass, that is dm, which is times the centripetal acceleration, which is minus rho omega squared x. Centripetal acceleration should be in the radially inverted direction. So dm is again, sorry, the acceleration is omega squared x. So dm is essentially rho a dx. This is differential volume, differential mass, and centripetal acceleration. So then you have a will cancel out from either side. Is it so? Yes, I believe E U double prime E A U double prime plus rho A omega squared x rho A omega squared x, and dx will cancel out, is 0. So this whole thing becomes your q of x. Okay, so solve this problem by taking two. Again, as you can see, your q of x is linear in x, which basically means the exact solution is cubic. So even if you try two quadratic bar elements, just like this case, you are not going to get exact solution but approximate solution. Quadratic bar elements of lengths. So divide the length rather, it could be 100 radian per second. Two quadratic bar elements of length. Actually, you can take uniform equal lengths of equal lengths. Solve for uys. So if you take two quadratic element, so you'll have total 5 nodes, 1, 2, 3, 4, 5. So 5 uys, and there would be two elements, u1 and e2. Now in each element, and stress at each node. So the stress uh, since the displacement is a, is a quadratic function, so the strain and the stress would be linear functions. So even in element 1, the stress would be changing from node number 1 to node number 3. Okay. So I need to plot all of them. Okay. And also compare with exact solution. Okay. So I need you to plot each of these displacements and stress values at each node, and mm, and also compare them with the exact solutions. Okay. Do you think this can be done?
So we have to try, sir.
Yes. I mean, the thing is, this would not happen in 5 minutes. You'll have to, mm, you'll have to put some time into it. Okay. And if you require to, solve matrices using MATLAB, go ahead and do that. Okay. See, I know you'd be getting a 5 by 5 matrix. Okay. And if you, once you get that, to solve that, you'll probably not be able to do that by hand. Of course, that 5 by 5 matrix will only have 3 as the common node. Okay. But still, you can take help of MATLAB uh, to solve the problem. Okay. Or even to do the plots. Okay. So try out these two problems. Okay. One more thing. At the beginning of the class, we said that why we do not go for higher and higher order polynomial. Instead, we go for refining the mesh. The reason is, you see, today we talked about getting the element stiffness matrix for two linear elements, and then assembling them, then solving them. Okay. In a 1 hour class. Whereas it took us a 2 hour class to establish the stiffness matrix of a single linear bar element and a single quadratic bar element. The point here is that once you know how to get the stiffness matrix, or what is the expression of the stiffness matrix for a linear bar element or a quadratic bar element, okay, you can repeat the process again. This repeating thing, just something that you can very easily code in a computer program. These are all the essence of finite element method. So you can repeat the process to construct the element stiffness matrix for different elements. Then if you know how many elements are there and how many degrees of freedom are there, and which degrees of freedom are shared between which two elements, then you can construct the global stiffness matrix. Okay. But instead, every time you see a more and more complicated problem, and then you go for a higher and higher order element, you see the derivation of the stiffness matrix. That is where the human contribution is. Okay. So that we do as a homework before writing the program. Now, if I see a complicated problem and decide to go for higher order element, let's say cubic element. Now, right now, I'm not ready with the stiffness matrix for cubic shape function. Then I'll have to do the derivation for, do a complicated derivation for a cubic shape function. Whereas I could simply put 10 linear elements, 10 lower order elements, simply by single command in a computer program, and probably get very close level of accuracy. Okay, that's why going for higher and higher order shape function is not a solution, because the entire formulation changes, and that requires derivation, human contribution, and then later that needs to be coded, and that's only when that is implemented. Or you can be ready with, let's say, a linear, a quadratic, or a cubic shape function, but then you cannot then go for the fourth order polynomial. What you can go for is, once you have the formulation for a single linear bar element or a single quadratic bar element, you can, without any human contribution, you can simply mesh a bar with 10 of those. You can go for mesh refinement much faster, much efficiently, compared to your polynomial upgradation. এই পার্টটা কি বোঝা যাচ্ছে কি বলতে চাইছি? বোঝা যাচ্ছে না?